Right, so this is the next section of the physics monologue. Now, what we're going to be doing today is, this is the main video of optics. This is about Snell's law and refractive index of materials, how to work out the speed, the changes, the wavelength changes, and yeah, basically Snell's law. We've still got waves, and if we're going from the way I recorded it, springs, moments, etc. So this is basically the main crust of it, as I said. Now the main equation you need to know, we're going to go right from the start of optics. Yeah, so you probably know this from GCSE formula. So sin I over sin R, yeah, equals n. Then you go, oh, how did that come about? You just think of that one day, you thought, you know what, I'll give that a go. Well, it's from Snell's long law of n1 sin I, I equals n2 sin R. And you've just rearranged it to get that, assuming that, you know, so the refractive indexes, etc. Yeah, so that comes from that. That is the basic for Snell's law. And we can just rearrange that to find incident angles. Yeah, just find that to find incident angles. I will give you some questions at the end of this DVD. You can have a quick snapper and have a go on. So if we've already said that equals M2. So N could also equal C over CS. Then you go, well, what's C and what's CS? Well, I think you'll find that C is speed of light in a vacuum, which is... Nope. Yep. Possibly. Because I didn't hear you there. You know, as far as I am with technology, I'm pretty sure you can't speak to the camera. I did try doing that once. Anyway, so it's 3 times 10 to the 8 meters per second. So that is what we call a constant. You probably already know that, but I do do so. 3 times 10 to the 8 meters per second. CS, now that is varied because that's the speed of the material. That is the speed of light in the material that you're measuring. That is there's one material. Let's say that's going from air to glass even. You know? That'll be the speed of light in glass. If you've got the refractive index of glass, say for example, is 1.5, and you want to work out the speed of, let's do that calculation actually. I've done calculations for a while. Saying you're working out the speed of light in glass. Let's just do it now. We don't need a high-tech thing. All we need is a calculator. Which probably, I'll find it just after I stop recording this DVD. As soon as I hit the pause button, I'm sure it'll pop up. Yeah. So, I must have put it somewhere. Doesn't bode well, this does it? Right, anyway, so if you wanted to find the speed of light, you just swap it around. So 3 times 10 to the 8 over 1.5 equals 3.5. So equals 2 times 10 to the 8 meters per second. Because 3 over 1.5 is 2. Pretty sure. Yeah, 2 times 8. So that's the speed of light in glass, which is, as you can see, quite different to the speed of light in. I mean, it only looks like 1 times 1, but it's actually 1.10. 1 times 0 times 10 to the 8, which is quite a lot meters per second. So that is how to work out the speed of light in a material. Now this is also connected to the wavelengths, because C equals F lambda. Now when a light ray goes into 2 different materials, the frequency does not change. However, if the speed changes, then that can only mean one thing, that the wavelength changes as well. So that we can put it into this equation, y over y lambda s, lambda over lambda s, which is the wavelength in the speed of light over the wavelength in the substance. Now you can work out the wave of light by simply putting 3 times 10 to the 8 into that equation there and simplifying it down, etc. if you know the frequency of the speed of light. And obviously that will allow you to work out the wavelength in the two substances, which it might ask you to do. It might not, but they're two key equations. Hopefully you've paused the video and got that down. I'll leave them two Snell's law on there, but just to make a bit more room for us. Yeah, I think there's just a few more bits and bobs we need to go over, but that is the main bit. So I sort of said it before in my total internal reflection video, or if this is the first time you're watching an optics video, then I'll go over it now for your benefit. So when a material, just a few things you need to know. So I'll draw a diagram here. This is N1, N2, and then this is the normal. So let's assume that it's going into material with higher refractive index. So N2 is greater than N1. However, it's so total internal reflection can't happen here, which I will explain in my next video, but it can't. So it goes through the two materials, and because N2 is large, it's been slowed down by a greater amount. So that means that it's been slowed down more towards the normal. Sorry, that's what I was going to say. Yeah. So if it's slowed down more, it's a sudden deceleration. It's almost instant as it hits that material. It's going bang, straight to bang into that material. So it goes straight into that material, and then yeah. So it slows down by a greater percentage. So it goes more towards the normal. Doesn't really matter how I draw it on there, as long as you put the correct angle in when you're figuring it out in the exam. As long as it's more towards the normal, start that method about the angles. So yeah, and then when it goes into a material of a some rubber of a lower refractive index, it does the opposite. It bends away from the normal. So this is assuming N1 is greater than N2. Because when it leaves the material, it speeds up again, because it's less resistance, if you can imagine it that way. So let's get rid of that. Oh, damn it, here. So I'll get rid of them. So, I'll just write some questions up now for you, and you can have a go at them. Obviously this is assuming you've watched the whole video. Okay? There's just some questions from the book and I'll write it up for you. So, I won't write the whole equation out, the whole question out, I'll just write the important bits for you. So you don't have to read my whole writing. So, F equals 4 hertz. Frequency is measured in hertz, by the way, I should have said that. It's travelling at speed, so C equals 0.16 meters per second. Across the boundary from deep to shallow water, where the speed is 0.12 meters per second. So that's CS. So that's deep to shallow. So that's deep. Shallow. Calculate the wavelength of these waves. So in deep water, so lambda in deep, and lambda in shallow. And then the next part of that, the instant wavefronts So sin I, oh sorry, yeah, I equals 25 degrees, and you need to work out R, and this is the same part of the question, by the way. I'm just simplifying it down, getting rid of all the words so you can just pick out the key information. And this one, next one is what we were saying before about the speeds. So, speed of light in a vacuum is 3, this is the second question, 3 times 10 to the 8. Calculate the speed of light in glass. So n equals 1.52. Sorry, 2. And you want to work out CS. And 3. Oh, sorry. 2b. I'm just going to put this last question. And n equals 1.33. This is for water. You're working out the speed of light in water. And C equals 3 times 10 to the 8. Work out CS. Now, if you do want me to, that's just a few simple questions for you to have a go at and see how you get on with the simple stuff. If you want a bit more advanced stuff about like calculating critical angles, for example, and just post a comment in the video and I will more than happily send you some your way. So hopefully that's answered everything you need to know, and see you in the next video.